The purpose of this section is to familiarize you with the concept of hydrostatics and solving problems related to hydrostatic pressure. First, let's take a quick look at a review of pressure. In the last chapter, we looked at stress as a force per unit area. Stress applies to solids, but here, since we are looking at liquids and gases in this unit, we are going to use the term pressure instead of stress. So pressure is also a force per unit area. Some units for pressure are newtons per meter squared, which is the same thing as a Pascal or capital PA in the metric system. Pressure can also be measured in pounds per square foot, which isn't very common, or it can be measured in pounds per square inch or PSI in the English system. Hydrostatic pressure is the pressure that a liquid at rest exerts on a submerged object. By definition, we are not looking at liquids that are flowing or moving, they must be at rest. This hydrostatic pressure is exerted uniformly in all directions, as we can see by the arrows pointing to our rock. All of the arrows are the same length. The pressure in a liquid only depends on two things: the depth of the liquid and the weight density of the liquid. Keep this idea in mind when we take a look at the equation for hydrostatic pressure. Before we look at an equation, we are going to look at a couple of examples where you may have experienced a hydrostatic pressure before. First, if you are swimming in a pool that is maybe 10 feet deep, there's going to be a lot more pressure on your ears when you are swimming near the bottom of that pool than when you are swimming just along the surface. You may also experience hydrostatic pressure in your head when you hang upside down. Blood tends to pool to your head, and since blood is a liquid, you experience an increased hydrostatic pressure in your head. Another example of hydrostatic pressure would be in constructing a dam. As the water depth increases, the hydrostatic pressure also increases. Since the pressure at the bottom of the dam is much greater than at the top, dams are constructed so they are thicker at the bottom than at the top. Otherwise, the hydrostatic pressure at the bottom of the dam might be too great and the dam could crack and fail. One last example of hydrostatic pressure would be if you have a barrel of water and you poke several holes that are exactly the same size. The hole at the bottom will shoot water out farther than the hole at the top, since the hydrostatic pressure is greater at the bottom than at the top. You can even try this demonstration at home with an empty milk jug with 3 holes. Even though the distance between holes in this case isn't that great, there is still higher pressure at the bottom than at the top. Now that we have seen what hydrostatic pressure is, let's take a look at the equation to calculate the hydrostatic pressure. Remember, before we said hydrostatic pressure depended on two things: the depth and the weight density of the fluid. Therefore, this means that the pressure is equal to the depth multiplied by the weight density of the fluid. In your notes and in this table, you see that weight density for some common liquids. In this table, the middle column is the weight density in the English system, and the right column is the weight density for the metric system. In the English system, our units for pressure are pounds per square foot, with the depth measured in feet and the weight density measured in pounds per cubic feet. In the metric system, the pressure is measured in pascals, or newtons per square meter, the depth is in meters, and the weight density is in newtons per cubic meter. In the next video, we will look at a couple of calculations with hydrostatic pressure.